Okay, so everyone is pretty much ready. We continue from where we left yesterday. The second part of the Variational Inference and Optimization series. I'll start with a very brief recap of what we talked about yesterday. So you should still remember until you stayed up too long. So what we're talking about is instead of something like MCMC, what we are trying to do is that we're solving the Bayesian inference problem with optimization. We assume a parametric approximation, some distribution Q, and we simply find the parameters of this approximation so that they are close to the posterior of interest. How we do this is we assume the Carlo divergence between the approximation and the posterior as a learning objective, trying to minimize it. But in practice, we convert it into a maximization of a lower bound for the log probability of the data. And it simply consists of two different terms with two completely equivalent formulations. So either you have the expected joint likelihood plus the prior, the entropy of the approximation, or you have the expected conditional likelihood and a divergence between the approximation and the prior. It doesn't really matter at all. The only difference between these is that we are throwing around this prior term on different sides of the. Both of these terms are expectations. So this is what we do. And what we usually do is the mean field approximation. So we assume that the approximation factorizes into smaller terms, either for every variable independently, or then it is generalized mean field approximation. You can have multivariate approximations there. And then we do coordinate ascent, which means that we pick one of these approximating terms at a time, and we simply compute that the unnormalized value of this approximation is e to the power of an expectation of the log density over every other term. So we write this in two different ways. I raised yesterday the rule, but it's a very simple, elegant rule. And if we are really talking about models with conjugate, conditionally conjugate models with conjugate priors, you can actually compute these, or write down the equations at least in a very compact manner that is independent of the specific distributions that you are using. And the expectation can also be written as kind of the conditional distribution of this parameter given all the others. The problems with this approach is that it's really rather tedious process of deriving these and make a lot of mistakes. But more critically maybe that we are really limited by the scope of things we can do. We need to assume the mean field approximation. Going beyond that is really very hard. And we can only compute these expectations in closed form if we really have these conjugate models. And what we would want to have is that if we want to use variational approximation for a rich class of models, rich class of approximations, we would want to get rid of all three of these issues. Have something that is easy to use for everyone. You don't make any errors. You don't need to do any tedious integral calculations. And you can use a rich family of approximations for rich family of models. This is currently happening. We can mostly get rid of all of these. But it's still in some sort of transition state. The earliest solutions are kind of 4 or 5 years old. But just to motivate this, let's take a detour and see what has happened in the transition from good old-fashioned neural network research to the current deep learning research. I actually started my own career working on as an intern, as a bachelor student, where the first task I was given was to trace some kind of a multilayer perceptron for a density estimation task of estimating the probability of the class distribution for a given input. And what I did was actually that I started by manually deriving the backpropagation gradients for MLP. Then I took up MATLAB and started writing the model, propagating gradients, and then implemented conjugate gradient algorithm for training this MLP. And it really took me a summer. The result was a horrible one, then it was a bit slowish, we switched to C and rewrote some of the conjugate gradients there and everything like that. This is how you would do it today, roughly like this at least. You pick up a platform, Keras, TensorFlow, PyTorch, doesn't matter what you do. You specify a model. Okay, I have the simple MLP, one hidden layer of n units. I specify my activation functions, and then I just ask, please optimize this. It doesn't matter, so what's behind this is, I would first of all argue that this is the biggest reason for the current deep learning hype, not the computation power, not the algorithmic improvements, not the amount of data, but the fact that everyone in the world is able to build these models with relative ease. And the big things here are that, there is a good quality optimization library. You don't start from scratch trying to write conjugate gradients with all the line searches and everything. And it's model independent. You don't do any derivations for the specific model that you have. Instead, you just specify the model. And on the background, the system is computing all the derivatives you need for some sort of gradient-based optimization. Who knows what is automatic differentiation? Not too many of you. Then it's a good thing that I'm running up. So what's happening is that in order to actually optimize this, we need gradients of this neural network here. Derivatives of every single weight of that, derivatives of the loss function with respect to every single weight of this neural network, which is computed with the backpropagation algorithm. How many of you know what the backpropagation algorithm is? Good. Then you also know what automatic differentiation is because it's the same thing. It's just a more general formalism. So assume that you have a function, any function, that is mapping from a d dimensions to a scalar value. Any loss function is like this. There is the loss. Log probability of the model is a scalar function, so this is kind of, all the loss functions essentially look like this. There is an algorithm called reverse mode automatic differentiation that allows you to compute all the partial derivatives of this function with essentially no additional computational cost compared to having actually compute the value of the function. This is somewhat surprising, and it's an automatic procedure that doesn't really require anything. So it means that all the effort we used for learning how to differentiate complex functions is kind of pointless because we can always solve them with the automatic differentiation instead. The basic idea is that what's happening is that we split the computation of this function into some simple elementary functions. We store all the possible intermediate results that we compute during evaluation of this function, and then we manipulate those results and the derivatives of these simple computational steps that we always know they are easy things. We manipulate those in an efficient manner to create the eventual derivatives that we care. And this is actually exactly what happens in a backpropagation. You go the forward step. You compute a lot of stuff while you are evaluating the value of the input for this neural network. You store all the intermediate results there, and then you have these equations that tell you how to efficiently propagate the error signal back from the end of the network towards the beginning. I'll show you an example, not related to the backpropagation, but for a simple function of two variables. So what we have here is that we have a function of two variables, x1 squared plus cosine of x to the third power. Doesn't matter what the function is. This is an example showing that we can't compute derivatives of this function with respect to x1 and x2 without any sort of complicated chain rule type of manipulations or anything. So what we do is that first we see how this function is computed. The first thing is that we need to square the first argument. What we do is that we give it a new name. Say that it's a third variable in our model. Its value just happens to be x1 squared. And at the same time, we record that what is the partial derivative of this x3 with respect to x1. That's an easy thing to do. We know that it's a simple elementary function for which we know the derivative. Then we follow the computation. The next thing you need to do is you need to compute this. And we again give it a new name. And we store the derivative. Again, it's an easy derivative to compute. Then the next thing is, this is where it gets slightly more interesting. We need to compute this. We don't compute it from scratch. We say that the value is actually cosine of the x4, a variable that we have already computed. Doesn't make any sense to recompute it. We know what its value is. And we give a new name for this. And we store the partial derivative again. It's as a function of x4. It's not related back to the original inputs of our function. And finally, the summation is easy. The derivatives are just once there. Now we've computed the value of our function. x6 is exactly what the function value is. Now we can go backwards and compute all the derivatives of this function with respect to all of these variables, both the original ones and the new ones that we introduced in the middle of this process. The derivative of f with respect to x6 is just 1, they are the same thing. But then we start computing. We take a look at that. We want to compute the partial derivative of our function with respect to x5. It has to be, according to the chain rule, its derivative with respect to x6 multiplied by the derivative of x6 by f5. And then we just need to consult here. This goes here, and the result is 1. That's kind of not very interesting example. The next one, we need to say, take a look at this. We know is 1 coming from here. And then the other term we again could check here, it needs to be sine of x4. So the partial derivative of our function with respect to x4 is just, no, it's not x4, it has to be x. Yeah, it's sine of x4. Yeah, that's correct. We proceed like this until we reach, at some point, we reach a partial derivative of our function with respect to one of the original inputs. And we can compute it by looking at this previous thing here, and then this thing from here. And similarly for the first argument. The important thing here, in this simple example, we could have directly looked at this original function and computed the partial derivatives. We would certainly know how to do it. In a more complex example, like a neural network or a complicated probabilistic model, that gets very tedious. If you have nested functions of error cancel, it's very difficult to compute it. And the important thing here is also that we are actually reusing values that we computed while we were computing the function value. So there's no nested summations of any kind, so you don't recompute anything again. I don't go into the details, but in practice what you can do is that you can augment whatever code you use to compute the function. You can essentially augment this code by storage of these partial derivatives and intermediate results, and as an output, automatically generate code that also produces the partial derivatives. And this kind of comes almost with no additional cost. It's roughly on the same order of magnitude as having computed the function value itself. So this is essentially what is behind the deep learning, possibility in deep learning of writing just the model and not needing to worry about its gradient. It just means that somewhere under the hood there is functionality for performing this automatic differentiation of any differentiable function that only builds on the only thing they needed to do is essentially write down these rules and then all the elementary derivatives of these elementary functions. So we need to know that the derivative of sine is cosine and so on. So this is what's happening. You don't need to understand exactly what's going on. You just need to trust that if you have a differentiable function, then computing its derivatives with any of the inputs that you can think of is kind of an automatic process. Okay? The other part of the deep learning transition was that, Given a model, we can now compute the gradients. The other step is to optimize the parameters of the model using those gradients. And for this, we use the ancient algorithm of stochastic gradient descent. So you have some sort of a loss function, which in most cases is simply something like this. You have a data set with n examples. Your loss factorizes over these individual data points. It's a classification problem or something. You feed in one input, you compare the output to the true value. So you have a loss that is some sort of a sum over the data instances. And what stochastic gradient descent, instead of regular gradient descent, means is simply that we estimate the gradients of our actual loss function by subsampling data. Here I wrote the equation of subsampling just one instance of the data. In reality, you can of course use mini-batches. And we just say that this is an estimate of the gradient of the whole loss function after having observed just one of the data. It's a stochastic estimate. It's unbiased. It has potentially large variance. Doesn't really matter. It's still an estimate. It roughly points to the right direction. And the stochastic gradient descent then simply modifies the current parameter updates by taking a small step against the gradient direction to minimize the loss function. This is kind of standard old gradient descent or stochastic gradient descent, dating actually back to 50s, the stochastic variant as well. There's these Robbins-Monroe rules of how the step length needs to decrease at a reasonable pace in order to not stop too early and in order to actually converge. The big thing in current deep learning literature is that you have adaptive control of the step length. The step length is usually also not a scalar parameter, it depends on the dimension and so on. But the important thing for us is that there's plenty of techniques for this, like AdaGrad, Adam, RMS prop, whatever. There's probably new ones popping up every month or so. Someone has thought about them. They are reasonable schedules for updating step lengths, so we can just pick up an optimization routine, use that, and hope that it works well. In practice, you would never ever want to implement a stochastic gradient descent library yourself, except for learning purposes. You will never get it right. It's extremely difficult to actually get it to converge well for an arbitrary model that someone else specifies in the future. But this is what's happening under the hood. A combination of these two things is what makes all the neural network learning kind of easy for us. It's not quite yet enough for all the improvements that we've seen, but this is the core element there. What is happening right now in the Bayesian inference community is that the concept of probabilistic programming is trying to do the same transformation for Bayesian modeling that happened essentially in this kind of going from old neural networks to kind of deep learning path. By simply providing an easy interface for specifying the model, something that looks like this. I just provide a structure of my neural network and nothing else. And then you have an automatic model-free inference algorithm that can be done for any model that you can write. Something like Stan is a primary example of this. I didn't actually put an example here, but you really specify your model by writing a small piece of the code. That looks almost like the mathematical equations. And in fact, this is not a new thing to do in some sense. So standard Bayesian inference algorithms actually always were model-free. If sampling, for example, is not, though you can actually cleverly manipulate it in exponential family to make it model-free. But Metropolis Hastings, the standard naive Metropolis Hastings algorithm, actually is model independent. You just propose changing your model parameters somehow, and then you use the log density, which we always can compute, to either accept or reject this transition. So it's the same thing as with neural networks. The backpropagation algorithm always was, in some sense, a model-free thing. It was just tedious to write a good software library that allows doing backpropagation for arbitrary neural network structures. Similarly, in the Bayesian inference, Metropolis Hastings is a universal inference algorithm that you can run on any model. It's just not very good. It's very slow, it's very fragile. So people actually wanted to build model-dependent things like deep sampling algorithms to improve. In practice, what's happening right now is that if you look at something like STAN, it's using very advanced Hamiltonian Monte Carlo algorithms that actually are very good. They don't work for all models in the world, but they work for a very wide range of models and are reasonably efficient. So this is what's happening on a general level. So we can build probabilistic models in a similar manner, not quite as easily as the neural network-based models. We still need to understand a lot more about the statistics, but kind of in a relatively simple manner. The question is, can we do the same for variational approximation? Is there a way of doing variational approximation in a model-independent manner? And the starting point is much worse. So backpropagation and Metropolis Hastings were always model-independent solutions. We just needed to make them easy. For variational approximation, everything that we've heard up to now is that, no, there's no chance. We don't have even the basic algorithm of doing any kind of variational approximation in a model-independent manner. What we would want to do is still achieve that. So we need to start by inventing the algorithm, not just by making an existing algorithm easy to use and offering a good software solution for that. The answer is yes. I wouldn't be having here this other part of the lectures if the answer was no. We can do that. We can build practical variational approximation algorithms, essentially building on the exact same tools that we are using in the deep learning, so automatic differentiation and gradient descent. If we are willing to make some assumptions that are not completely innocent but are still reasonably mild. There's two alternative set of assumptions that we can make. I cover the technical details corresponding to both of these. I don't actually show any very concrete examples today because I believe you will be going through those in the afternoon anyway. So the first assumption is that the only thing we assume is that the approximation itself is differentiable with respect to the parameters. For any sort of a continuous approximation, it pretty much anyway holds. So if you're approximating something with the normal distribution, then of course you can differentiate it with respect to the mean and variance of the distribution. So this is a very, very, very mild assumption. The other assumption is that we assume that the model itself is differentiable with respect to its parameters. And furthermore, very technical thing that we can reparametrize the approximation. I will get back to that once I explain what reparametrization is. But about the first part, we can already talk about. This is, for example, what STAN assumes anyway. Hamiltonian Monte Carlo builds on gradients of the log density. So this is the same assumption that we are doing for efficient model-free MCMC. So if your model falls into that category, then everything is fine. If your model, for example, has discrete parameters, then things are not fine. You need to analytically integrate them out in order to make it differentiable. So you can certainly train things like mixture models that have discrete parameters in STAN with gradient-based optimization. You just need a bit of trickery. But these are really the things we need to assume either one of these. I'm not aware of any technical solution of getting forward without one of these assumptions. And I don't think anyone else knows either. So let's take a look at how do we actually do this. So our loss function is an expectation over the approximation. So any expectation we can always approximate with Monte Carlo, meaning that we just draw samples from the approximation, this theta n, and we compute the average of the function over these samples. The average log ratio of the joint density and the approximation. This is a bit unbiased estimator for the lower bound of this evidence. It's not actually a very good estimate for the marginal likelihood at all. I will get back to that towards the end of the lecture. But it doesn't really matter. For the bound itself, it's a reasonable approximation. So we can convert the evaluation of our learning objective into a stochastic estimate. We don't need to compute analytic integrals over Q to estimate our objective. This is actually something you could already use to debug a coordinate ascent variational inference. You've written your function for computing the evidence lower bound. You can also write a Monte Carlo estimator for that and see that they match. If they don't match, you probably made a mistake in one of these. Almost like, most certainly in this analytic derivation, it's much more complicated than this. But to optimize this, so what we would want to do is use gradient descent, stochastic gradient descent typically, where we would have be able to update the parameters of the approximation by taking a small step towards the gradient direction. So the sign of in this gradient, so that's gradient ascent now, we are maximizing the function, but it only changes the sign of the gradient, nothing else. And this is what we need to do. The two parts we needed for kind of automatic model-free inference in deep learning was that we need to be able to evaluate the gradients with automatic differentiation, and then we need to just update them. Here, automatic differentiation, of course, works exactly as it would in any other case. If we can differentiate log of p or log of q or something, we can use the same piece of code for computing the derivative. But the tricky part here is that our loss function is an expectation over the q. This is the difficult part. Let's start simply trying to do that. So I'm dropping now, for simplicity, all the time, I'm dropping this part here. That's the entropy of a distribution. So Q log Q would be the minus entropy of the distribution that we've chosen. That usually can be handled analytically, even an expectation of the expected value. So there's no issues with that. I'm dropping it for simplicity on this notation. We just need to remember that it exists there as part of our gradient as well. So what we have is that we are looking at our expected log likelihood, the joint log likelihood of the model. We want to compute the derivative of that with respect to some parameter of our approximation. You can change the order of integration and differentiation. In this case, at least, you can almost always change it. If you're a mathematician, you really can, of course, think about reasons why not to. But we are talking about well-behaving, nice probability distributions. We are never going to be in the regime where this is not valid. So this expectation is simply an integral of q times log p. We change the order, we take a derivative of that, we change the order. So it's an integral of derivative of q times log of p. This is perfectly fine. We can write this down, but it's still an integral that we would need to analytically integrate because it cannot be approximated with Monte Carlo. So the idea of a Monte Carlo approximation is that you need to have an integral that is an expectation of something. So it has to be an integral of q times something. And this is not. It's an integral of gradient of q times something. It's not an expectation. You cannot approximate it with Monte Carlo. You can't just draw samples from Q and plug them in here. It doesn't mean anything. The Monte Carlo approximation is only valid for expectations. But there are two ways of converting this into something we actually can compute using Monte Carlo. They're called the score function estimator and reparametrization. I start with the score function estimator and then move to the reparametrization. The score function estimator, unfortunately, the derivation of that is somewhat technical. I don't think, there are probably intuitive explanations for this. I decided to put here the purely technical derivation. So, This is what we have as the definition. This is what we did on the previous slide. The integral of a gradient of q times log p. Now what we want to do is that we want to rewrite the gradient of q as something that looks like an expectation. And what we get is that this is a way to do it. A gradient of any function is actually the same thing as the function times the gradient of the log of that function. So this comes from a very simple rule that what we have on the left-hand side. We all know that if you take a derivative of a log of something, it's the derivative of the inner function divided by the function itself. We've just reordered the terms here. So this is simple identity that is already kind of high school math. If you forget about the fact that we're talking about vectors instead of scalars and so on. So what we just do is that we plug in place of this, we plug in the rule here. What we have is, there's the log of p, then what comes is a q times the gradient of log of q, which now suddenly is an expectation. There is q, it's an integral over some things times q, and it's integrated over theta. So it actually is an expectation over q of log of p times the derivative of log of q. Now it is an expectation, so we can use Monte Carlo. Draw samples from q. For every single sample, you compute what is the numerical value of a log, the log gradient of log of q multiplied by the log of p. You can also think of it as that if you kind of think of log of p as a weight, you're computing the expected gradient of the log of the approximation multiplied by some weights that come from the model. This is clear? Okay. So this is a way of estimating the gradient that we need. Yeah? Let's see. I will actually. So no, I just kind of wanted to clarify actually an aspect that I'm going to show here. That if we think about log of p, it acts as, so what we are doing is that we are averaging off these gradients of the approximation. The only thing that log of p influences is how much weight we put on each of these. It doesn't change the direction in any way. So you could think of it as a weighted average of gradients of your approximation. The weights depend on your model, but this is the only way the model appears in the gradient calculation. It's already kind of starting to sound stupid. So this estimator is valid. It's a Monte Carlo estimator for the gradient, but there are some real problems. I mean, it has actually extremely large variance. So it essentially means that m has to be extremely large in order to get a reasonable estimate. So like I already, based on this discussion, it's like that the model has no effect on the direct effect on the direction of the gradient. We are looking at gradients of our approximation. We are weighting them somehow, depending on the model. But that's the only way the model influences this gradient. Furthermore, the range for log of p can be extremely large. So there can be one theta for which the probability of the data is very high, and for the every other one that is very small. Then essentially this estimate happens to rely only on this one of these theta. And we would of course want to have a large n to be able so that it doesn't really depend on just one of these. So I saw some examples that hopefully clarify this. So what we're doing here is that we have here the solid line is the posterior that we are trying to approximate. And the dotted line is our current approximation, which for simplicity here has a fixed known variance. So the only parameters of the approximation are the mean of this thing. We are just trying to shift it on top of this true posterior. So what we do in a Monte Carlo estimate is that we start by drawing one data point from this approximation. Sorry, not data point. So one particular value of theta m from this approximation. This is what's happening. Then what we do is that we take a look at the gradient of this. So where should we move? To which direction we should move the approximation so that the approximation would give a large probability for this sample that we drew from there. That's kind of the direction of the gradient. It actually kind of starts, so I'm drawing the gradient here so that it starts from the point, the theta n. That's kind of just for illustration purposes. It will become clear sooner. This is the gradient we compute. So it's the gradient of log of q. Then this is being multiplied by the weight that comes from whatever the log of the actual probability happens to be. Log of a probability is usually a negative number if the probabilities are small enough, so it actually ends up changing the direction of this. So what it says is that if we take this one sample approximation, then the derivative that enters into this calculation of the Monte Carlo estimate, now shifted back to where the actual center of the distribution is, it is this green arrow here. This one sample that we happen to draw suggests that the gradient should point to that direction. The rightmost plot is forget that, it's going to be the actual estimator that's based on averaging multiple of these samples. And scaling is slightly different. So here it's just averaging over this one sample that we've drawn. And scaling it slightly different so that we see more details there. Then let's take a look at what happens when we draw more samples. So if we draw another sample, this time here, the derivative of where should we move, to which direction we should move the approximation to best capture this particular sample, it kind of again points away from the center of this distribution. The weighting it by the log of p flips the sign and scales it somehow. And what we have here in the middle, we're shifting, just drawing these two gradients that correspond to these two data points. That how do they try to influence the approximation? And the average of those two is this one. It's pointing to the rather wrong direction, but not terribly bad. Let's continue. Add a third data point. Happens to be somewhere on the right-hand border of this. So the red arrow would be pointing towards the window. No, sorry, not towards the window, the other side. And then the flipped gradient weighted by the log of p happens to have a very large magnitude, pointing towards the right direction. The average of these three is now pointing roughly to the right direction. So over there, I'm just mixing it up because I'm looking at the wrong thing. So it is really pointing towards the right direction, and the magnitude has suddenly grown a lot, even for this average gradient. If we keep on doing the thing, what we see is here we have, I think, 10 of these data points. The actual gradients point, if we draw the gradients from the data point, they kind of point towards the middle of the approximation. This is what they try to do for the approximation. So each one is pulling it to a relatively random direction. And the mean of those now here after n equals 10 is starting to point roughly to the right direction. So we can compute the derivative with the stochastic estimate by sampling data points from our approximation and just using these rules blindly. So it seems to be doing okay. The problem really is the variance. So here what I'm showing is that in every plot I'm having a couple of example estimates that I have obtained with sampling in the first one 5 data points from this approximation. So we're using m equals 5, and I just did it 10 times for different samples. It actually turns out that here that a couple of them point exactly to the wrong direction. and the variance is huge. So m equals 5 is definitely not enough, even for this very simplified case. It's a two-dimensional posterior, it's a two-parameter approximation, both are normal distributions. That's pretty much the simplest thing you could ever imagine. If I increase m to 10, yeah, still a few cases that happen to point to a completely bad direction. M equals 50 starts to look a reasonable thing. So you need to draw a large number of samples from the approximation to be able to estimate even this very simple gradient. All of this, evaluating it for 1 theta, may be complicated. So if you think about what's happening here is, this is the log density of the whole model. It may be arbitrarily slow to compute. You may have 10,000 data points and you're, say, a high dimensional, you need to do whatever you need to do here. And what we are saying is that just to evaluate the gradient, you need to draw 50, 100, maybe 1,000 copies of these thetas to be able to compute the gradient. And then you take one gradient step in an optimization algorithm. That's not very nice, but it can be done. This kind of algorithm is called black box variational inference. It's a black box algorithm. You can give it any model that you want to. So that dates back to 5 years ago. That you really just use this core function estimator to estimate the gradients. It's a very elegant algorithm in some sense, but I mean, if you forget about the practical value of it, you can, I would say that this is your kind of example of having an algorithm that is model-free, but is not efficient. There are practical things that you can do to make it more efficient. This already comes from the original paper, something called control variance, for reducing the variance of this expectation. This is a standard idea you can use for any expectation. So if you want to compute an expectation of some function, you can, due to linearity, you can just subtract any other function from this f, as long as you put back the expectation of this function again. So now if you actually know g of x, for example, deterministically, the second term here, you know the value. So you don't need to really worry about this term. And what you can do is that you can try to search for such a g that the variance of this estimator is smaller, variance of this expectation is smaller than what the variance of the f would be. And you get that essentially if f and g correlate heavily, but you can still compute the expectation over g in a closed form. That's a kind of general idea of control variance. What is proposed for the black box variational inference is to use a specific type of a control variant, which is actually, the control variant is the gradient of log of the approximation itself. This is now not multiplied by the log of p. We're just saying that let's use as a control variant this. The reason why this is being proposed is that the expectation of this term alone, so the one that we need here, actually turns out to be exactly 0. So this is a control variant for which the expectation of the control variant itself is 0. It can be seen by, again, using the same log derivative identity we used for deriving the gradients. That's not actually very interesting. What it matters is that because we know that this is 0, then the only thing that remains is this. And in our case, we chose this control variant so that it's simply some scalar multiplied by the derivative of log q, and our actual function was log p multiplied by the gradient of log q. So what we can see is that instead of the original expectation that we were computing, we can subtract or add an arbitrary constant for all of the log of p. For every log p, you can actually do whatever you want to. You can add, increase or decrease them by a scalar. It can also depend on a data point. So if this log of p actually factorized over data points, so if the c can also be a function of the data point and so on. I'm not going into the details here. But the basic idea is that there was kind of rich which family of transformations you can do for the log of p purely to trying to reduce the variance. So the mean estimate here is going to be the same. It has no effect on the mean of the, this value, but you can choose C to reduce the variance. Here's a simple example with m equals 10. That definitely was not enough in the previous example. With 3 specific choices for this kind of a control variant. Here there is no control variant. This is what we already saw. If you happen to choose your control variant cleverly as -6, you get this. This actually looks much better. -6 here, that's an arbitrary value I chose. But it does come from a kind of distribution of the values for log of p. The log of p here is in the range of roughly -10 to 0, the mean being something like 4 in this particular case. So I'm just shifting all the log of p to be somewhere close to 0. Getting rid of this issue of some weights being very large. It also changes the sign of the weights for some cases and so on. There are a lot of papers on proposing practical ways of doing control variants for different kind of models and so on. I'm not going into those, I just remind you that this is an important thing. Even a very, very minor transformation of adding a constant to all of log p has a dramatic effect. Okay? Let's see. Oh, it seems that I did something stupid for the slide as the last thing, doesn't matter. Let's then talk about the other alternative. The other alternative is called reparametrization, and I can already now tell that this is way better. This is going to have much smaller variance in estimating the gradient. But this actually also requires more. This requires having the model that we can differentiate. But anyway, let's start with the idea of reparametrizing the approximation itself. This is also, I think, in statistics called centered parametrization. The basic idea is that if you have an approximation, let's say a normal distribution over theta with some mean and some variance, we can equivalently write it as a distribution where we first sample from a standard, well, let's look at this example, I think it's better. We first sample a new augmented random variable from a standard distribution, 0 mean unit variance distribution, and then we transform the result of this sampling process into the actual observation. This is actually, that's what is missing from the last slide here, is that this is how sampling from a normal distribution is actually implemented in all programming languages. You sample from a standard normal distribution, you multiply the result with the kind of standard deviation, and then you add the mean. But this is a more general procedure. So any probability distribution that can be reparametrized can be written in this kind of a format. You first sample from some standard distribution that is not a function of our parameters. It can be the standard normal. It could be, let's say, uniform distribution for between -1 and 1 or something. That simply does not really relate to our parameters of this approximation at all. And then what you do is that the actual parameter, any sample from this distribution, is obtained by transforming a draw from this simple distribution with our model parameters. And that's a deterministic transformation. There's no stochasticity in this process. The normal distribution example is by far the clearest. It's not the only distribution that can be reparameterized. I'll get back to that. But the important thing is that all the stochasticity, all the randomness here is converted into randomness over a distribution that doesn't depend on our parameters, and then there is the deterministic mapping from these values to the actual ones. Once we have this, what we can do is that we can rewrite our expectation of interest, this is the expectation over Q, as an expectation over this standard distribution phi. It's an expectation over a distribution that we know in advance. In the normal distribution case, it's the standard zero mean unit variance distribution. And then what we are simply doing is that we are evaluating log of t and the parameter value, that is this kind of latent z value, transformed into the right parameter space by modifying it with the parameters. This is very nice. Our original problem was that we are taking a derivative of an expectation over something that depends on our parameters. But now the expectation has no relationship to our parameters. It's the same expectation over a standard distribution. Then we can just push the derivative inside the expectation. Doesn't really matter at all. It's an expectation over some completely different density. So what we have is that then it's very easy to use Multicolor Approximation. So you approximate the expectation by drawing samples from the standard distribution. Zero mean unit variance Gaussian. You sample these z's from there. Then for every sample that you obtained, you need to transform it into a sample that is obtained from our actual approximation with the deterministic function. But that's perfectly fine. And what this actually means is that we will need to be computing derivatives with respect to the model itself. Because in order to compute the derivative of this log density with respect to the parameters, we need to use the chain rule. We first compute the derivative of log of p with respect to the model parameters theta, and then we compute the derivative of the model parameters with respect to the parameters of the approximation. So this f, so theta is f of z lambda. So this really just means that in order, so even this is very nice, but in order to compute this, we need to use this chain rule. This is all kind of bad news, so we need to assume that our model itself is differentiable. It also may be slow to compute that. But it also is a very good news in a sense that we get much richer source of information here. Now the model itself has a chance of influencing the gradient directions, which was a problem with the black box score function estimator. And this is really also what's happening in the MCMC literature. So Metropolis Hastings algorithms, the simple naive algorithms, you're just sampling parameters, sampling a modification for your parameters, and then you're accepting or rejecting it based on just evaluating what the log of p is. Whereas the modern, efficient MCMC algorithms, Hamiltonian Monte Carlo or Langevin Monte Carlo or any of the other ones, they use gradients of the log of p as part of an MCMC algorithm. And it is way better. You just need to do it right. They're very complicated algorithms because it's actually difficult to plug in gradients into a valid sampling algorithm. But it certainly helps. And the same thing is happening here. If you are able to do it this way, then it's way better. The simplest example of what's happening really is this normal distribution. If your approximation is parameterized like this, it's parameterized by mu and standard deviation and corresponds to some normal distribution, then what you do is that you draw samples from a zero mean unit variance, and then you obtain theta by this standard simple rule. And if we now look at what are the gradients of our log of p with respect to these parameters, so I'm skipping the expectation part here. So you just compute first the derivative of the log of p with respect to the model parameter itself, and then the derivative of this transformation with respect to the parameter. Actually, for the mean, it happens to be that there is no, the second one is identity, the second term, there's no difference. Whereas the derivative with respect to the standard deviation, you just end up multiplying it with whatever the draw from the standard distribution happen to be. You just plug these into the expectation, and then you're going to go with that. Let's still solve an example of this before we can have a short break. So what is happening here is that I'm now drawing n equals 5 samples. These are the samples. And then I'm drawing as a green line the gradient of to which direction we should be pulling the approximation according to this particular theta or particular z that we sampled. And I'm again drawing them as some things that start from the data point, so that we see that they actually point all towards the center of the actual log probability, the log posterior, not the approximation. This is the mean of them drawn at the center of the approximation, which is kind of more intuitive way of thinking what's happening. And here I'm drawing 50 of these instances, the corresponding gradients for 50 choices of z or theta, and the average of those. The important thing that we see here is already that out of these 50, maybe around 1, 2, 3, 4, 5 point to the wrong direction. 45 of them point generally to the right direction. So individual single sample estimates are already reasonable. The final plot shows 5 examples where we have always n equals 10. They are all very good. They are all better than, let's say, they are comparable, but still I would say better than these with the carefully chosen control variant. Yeah. Oh yeah, so okay, this is the confusing thing that I'm using here. So a gradient is just a line. It's a line drawn from one point to another one. In this plot, I'm drawing them from the sample, from the point that was sampled, just to illustrate that this is. So in here, what I'm doing is that I'm shifting this line to start from here, so it becomes one of these. So that's just kind of an alternative viewpoint to what is happening. So I think the middle plot is what actually is the kind of natural, intuitive way of thinking about this. You are sitting there at the center of your approximation and you're checking that I want to go to this direction. I just draw the left one to illustrate that there is this technical relationship between that. From the sample itself, if you look at the gradient, it points to the kind of right direction. I think this would be a good time for a 5-minute break so that we can go to the technical details soon. Okay, let's continue. So now we are at the stage where I've introduced 2 practical ways of estimating the gradient of this lower bound by stochastically averaging over samples drawn from the approximation, either directly or via this reparameterization trick. And I've kind of shown examples saying that the reparameterization is clearly better than the score function estimator. The question is, when can we reparameterize these? Quite often, seems to be the case. I already showed an example of a normal distribution. You just sample from a unit normal distribution and make this linear transformation. A lot of other standard probability distributions, the code for drawing samples from those distributions is anyway obtained with a similar kind of essentially one-line expression. For example, an exponential distribution, you first sample from a uniform distribution between 0 and 1, and then you output logarithm of 1 over this value. Cauchy, sample from the same distribution, you output tangent of pi times that value. So what you can do if your approximation is a normal distribution, you know how to do it. If your approximation is an exponential distribution, you know how to do it, and so on. That doesn't hold for everything. For example, a gamma distribution, a beta distribution, do not account for this kind of a sampling algorithm. You don't have a simple base distribution from which you sample, and then a simple transformation of that, a differentiable transformation. You can still reparameterize those. So what the actual algorithm being used to sample from a gamma distribution in a typical programming language is a rejection sampler. You approximate the gamma with some other distribution, you sample from that, and then you occasionally reject samples because they don't really, the distribution you sampled from is not exactly gamma. They're actually very efficient, so you reject samples like once in 100 or 1,000 samples, so you almost always accept them. It is possible to reparameterize this idea of a rejection sampler in such a manner that you can still propagate derivatives through it. It gets a bit technical, but you can go and read the paper that explains how to do it. You can chain these simple transformations, so like a log normal, you first sample from a normal distribution, then you output e to the power of that value, and of course sampling from a normal distribution was originally obtained by sampling from a standard normal distribution and transforming that with the rule that we already saw. So that's actually the example here. So you can reparameterize a lot of stuff. There's also a recent thing called implicit reparameterization. I don't go into the details. It provides an alternative way of reparameterizing that is actually applicable to both of these families here. I don't want to go into the details. So the basic message is that most of the distributions that you can think of can be reparameterized. But of course, the other requirement for being able to use the reparameterization trick is the requirement of being able to differentiate the log likelihood of the model itself. But as long as you can assume this, and you're willing to operate with approximations belonging to this very rich family of approximations, then you can do this. In terms of programming, I would say that a year or two ago, if you wanted to implement anything like this, you would actually need to implement the reparameterization for this kind of stuff yourself. The ideas of how to do this are from 2017, 2018. To my understanding right now, for example, TensorFlow probability essentially implements the implicit reparameterization for some range of distributions that it supports. I don't know about Pyro, maybe someone else knows. The basic idea being that these tools are slowly being built in to the programming environments where we want to do these models anyway. So the reparameterization, I would foresee that in a couple of years at least, we can safely rely that if we have a reasonable family of approximations, then we can use something like this to estimate the expected gradient using the reparameterization estimate without needing to worry about what goes under the hood. This is what we would want to achieve anyway. I already actually said most of this, so if you just really compare about these two alternative approaches, the score function is very general. The only thing you need to require is that you can differentiate your approximation, nothing else. But it really has the issue that the gradients are not very sensible. So you need a huge number of samples to estimate the gradients, and you need to put some effort in figuring out good control variance. The reparameterization, it makes much more sense. We're actually getting gradients that point to the right direction, the mean of the posterior. And in practice, what people do is that you just use m equals 1. You just sample one z from this standard distribution, transform it into your theta, compute the gradient, and you quickly that. You can use larger number, yes, it's slightly more accurate, reduces the variance, but it doesn't make a huge difference as part of a practical optimization algorithm. So what we do in practice, when we talk about doing variational inference for a concrete model, we need to compute the gradient, and we do it kind of doubly stochastically. It's a fancy term, meaning that if you have this kind of a latent variable model, where you have some global parameters theta, then you have some observations xi, and some latent variables yi related to those. I switched from zi to yi because I'm using z on these slides for the draws from the standard distribution, but it's the same thing anyway. So what we do is that you approximate the gradient by replacing the expectation over Q with samples drawn from the standard distribution and then reparametrized derivatives. And instead of using the actual full logarithm of the joint density, we approximate that stochastically by looking only at the mini patch of the individual samples. So the prior over the parameters is there as it is. Then there is a sum always the data points in that mini patch for which we evaluate the log of p. And then we need to multiply it on the kind of right scale. So there's the n samples in total should actually be a small lowercase n divided by the number of samples in this mini batch to retain the scales of the prior and the likelihood. But this is very kind of standard approach. So it's just, you can safely mini batch over your data points. It also kind of justifies that, it's okay to be relatively inaccurate when computing the expectation. We are anyway computing the expectation over an approximation of our log of p. It would be somewhat weird that if you have, let's say, 1 million data points, you take a mini batch of 1,000, use that to approximate that what of your log of p is, but then you would suddenly use huge amount of computing power to be very accurate in taking the expectation over q. You're taking an expectation of a slightly different function anyway, so no need to bother computing the expectation exactly. So this is a general procedure for obtaining the gradient. Then everything else is actually relatively easy. So we get an automatic variational inference algorithm for doing variational approximation for any model that we can think of by first assuming a differentiable approximation, usually still factorized in some way. We also do assume now the functional form of every term in this approximation. We don't have the luxury we had in the coordinate ascent that the update rule will magically determine the functional form. You just need to say that, okay, I want this and this parameter, it's positive valued, maybe I approximate with a gamma. This thing here is a real valued parameter, I put a normal distribution there. There's a lot of freedom here. So we're switching the problem from worrying about the technical details into specifying the approximation that we want. You can try out different kind of approximations and so on. Then what you need, the next step is an algorithm for computing the gradient, or estimating the gradient. If you cannot assume anything else about the model, then you need to use the score function estimator. You put in, you compute the derivatives of the log of the approximation. That's easy to do with automatic differentiation. You just have whatever Q you have, it has some probability density, you take a log of that, feed it through automatic differentiation engine. Then you multiply these with log of the log probability minus some control variant, and then you put an effort to figuring out what kind of a control variant you should use. And that's your gradient. The better option is that if you can assume that your model is differentiable and that you can reparameterize your approximation, then just use the reparameterization estimate. This is an expectation over some standard distribution that doesn't depend on your parameters in any way. In both cases, I dropped this entropy term. Yeah?
This may be just pieces of approaches. Do the backward derivatives with respect to some subset of parameters, and then in the Variational Inference is the subset of parameters which taken over from inference.
This kind of hybrids, I can't think of any concrete examples right now. It probably can be done. It certainly can be done. There's nothing preventing you from doing that, but I haven't seen examples of that. Yeah?
So you thought that the only requirement for this transformation function is just previous to the differential, right?
Sorry?
The only requirement for this transformation of the parameter is function is previous to the differential.
It has to be differentiable, deterministic. Yeah, I think that should be enough.
Yes, but how do you come up with, for example, you have some arbitrary probability function, how do you come up with, so what kind of idea?
You don't. The answer is that you usually don't invent new probability distributions. What you do is that you start by saying, I want to, let's say, approximate this and this parameter with the Rademacher distribution. I don't know what it is, but it is a distribution that exists. And then you simply search for that. You realize that to sample from a Rademacher distribution, you have to sample first from a Bernoulli distribution and transform it like this. So these transformations, they are, for any given distribution, there exists this combination of a base distribution and a transformation that essentially exists in literature, assuming you can find a piece of code that produces samples from that distribution. To write that code, someone has to have figured out what this transformation is.
Yes, but my question is, so how do you search, like, what is the optimal way of searching through all these functions and probabilities?
Usually you don't do that. In some sense, let's say, most of the time you have a reasonable idea of what kind of an approximation you want to build. Like you really say that this parameter, I know that it has to be between 0 and 1. You probably say, I'm going to approximate with the beta distribution. This is kind of reasonable. Then what you would do in a real modeling pipeline is, of course, that once you've done this whole procedure, you start looking into your model. Okay, now something seems to be wrong. I don't really trust on these results. This is bad. Then you go on in some sort of a manual process of figuring out, maybe I can improve my approximation, or maybe I need to improve my model, maybe I have a bug in my inference code. You just need to start thinking about this.
So there is no simple thing.
There's no simple thing. That's actually one of the things that we are doing right now in Helsinki. We have a largest initiative on trying to formalize the workflow for developing Bayesian models with all of these stages that you specify a model, you do inference, you validate it, you go back to refining your model or refining your approximation and trying to make this really into something that you can formalize as you would formalize, let's say, a software engineering project. That's still currently almost completed still. Okay, so what I was saying is that these equations are ignoring the entropy part. The entropy part, you can either do stochastic estimation over that as well. That's very simple, or you can do analytic gradients over that. It doesn't really actually matter in most cases. And irrespective of which estimator you use, what we do is we do standard stochastic gradient ascent for optimizing our parameters of the approximation. You use automatic differentiation for computing all the derivatives that you need. Let's say for a reparameterization estimate, you need derivatives of the log of the probability with respect to its parameters, multiplied by the derivative of the parameter transformation function with respect to the parameters of the approximation and so on. You don't actually do this explicitly in any part. You just write your loss function, this stochastic estimator for the approximation, and then you pass it for the automatic differentiation engine. It takes care of doing the chain rule correctly anyway. You can use mini patches for evaluating gradient. It's a stochastic estimate, so you can just as well be stochastic over the data points. That's perfectly fine. It actually makes a lot of sense. And then you update the parameters towards the direction of the gradient, using all the possible tricks that are available in convex optimization literature. Don't do stupid things and do gradient descent with fixed step length or whatever. You can just as well start using Adam or arms prop or whatever. There's no guarantees that the heuristics built into these deep learning optimization algorithms are optimal for this kind of models. The models are different, the loss functions are different, but they are good proxies. You start with those anyway. I'm hoping that someone over the next few years does a proper survey on if you do gradient space descent in this kind of problems, what kind of convex optimization algorithms you should be using. But before that, let's just use any of the standard choices that people use in deep learning literature. Another approach, slightly different approach to doing this automatic inference, builds on actually transforming your model parameters. So here, you need to make an assumption of a specific approximation, and then you have this transformation corresponding to that distribution. Another alternative is to take your original model parameter, let's say something that is between 0 and 1, and would require something like a beta distribution as an approximation. You can instead first transform your parameter, the model parameter, to the whole real line with some transformation, and then you simply use a normal approximation. You use a normal approximation from a transformed version of your model parameter. As an example, so if you, let's say, have a theta, and you just know that one of your parameters is a scalar parameter that has to be positive. You could approximate that with gamma or exponential or something. Another alternative that is kind of very model independent in some sense is that you've just encoded as part of your software library a transformation that I express my original model as a function of theta hat instead, where theta hat is a free parameter, unconstrained parameter from -infinity to +infinity that can be transformed into this theta range or vice versa. There's always the kind of corresponding back transformation that if you know the theta hat, then you know how to compute the actual parameter theta. So this allows a kind of gets rid of the question of how do I figure out which approximating family I use for which of the parameters, but it replaces it with the need of figuring out a good transformation of this variable into something that can be approximated by the normal distribution. For example, for positive values, you could just as well use directly theta hat equals log of theta. It just turns out to be worse than this in most cases. But there is a flexibility of how do you choose these. And one more thing worth noting is that if you actually make this kind of transformations, then their expectations get slightly more complicated. You're doing transformations that actually influence the volume of the differential, so you need to have a lot of Jacobian of the transformation. I won't go into the details here. You can read them from the paper. But this is how STAMP, which actually has a variational inference besides the Hamiltonian Monte Carlo, it does variational inference this way. So you never ever specify a family of approximations. You just say you approximate things with a normal distribution. It allows you to choose between fully factorized normal distribution and a multivariate normal distribution, but that's the only choice you have. And under the hood, it is transforming all the parameters into a space where a normal distribution is a reasonable approximation. It is done this way mostly because this is how the Hamiltonian Monte Carlo works. You want for the Hamiltonian Monte Carlo, you want to live in a space that is unconstrained. So they always modify the model into this unconstrained space first, and then they can safely do Monte Carlo there. So they wanted to show you can do variational inference in the same way. The unfortunate thing is that it's not a very good approach. Let's say, if you have a conjugate model where you have some gamma prior and some normal, like some, let's say, a gamma likelihood and a beta prior that is a conjugate for that. No, that's not beta, that's exponential. But anyway, if you then do a variational approximation where you assume the corresponding distributions as part of your factorization, it actually is much better than doing this transformation-based approach. But it still works for simple models in a relatively automatic manner. You don't need to specify an approximating family.
Sorry.
Yeah.
So is it that in the previous case when we were using the Gaussian distribution as an approximating distribution for the full distribution, then our mean was unconstrained, our sigma was constrained. Are we talking about that?
No, we are not actually talking about that, but we're talking about whether the parameter that the real model parameter, whether that has constraints or not. So actually, yeah, you are right. So I've been skipping that in some sense that, okay, here, let's say, this parameter would need to be positive. That's a different kind of a constraint. That's a constraint we would take care of in the stochastic gradient descent phase. You would probably write it as e to the power of log of something. This actually, by the way, works even if you allow it to be negative. It doesn't really matter, it cancels out in this particular case. But in more, so this is a different kind of constraint. It's very good clarifying comment. So here we are really talking about transformations for the model parameters in order to not to need to specify a specific distribution. So it can be done. You just need to be wary. So if you write a probabilistic programming model on Stan and you do variational inference, there's no guarantees that it's correct. Luckily, you can always run the FCMC as well and somehow compare them. If they look the same, then you can proceed and, for example, put your variational approximation variant into production, saving a lot of computing time if you need to run it over and over again. But if you see that it's clearly worse than the FCMC, you can't rely that it's doing the right thing, and then you would rather maybe use the FCMC for future uses of that model as well. Then let's go to one more thing. This is called Amortized Inference. It maps to both of these estimators, so it's kind of an orthogonal dimension. So what we've all the time now been saying is that any approximation, any term in your approximation is parametrized directly by some lambda d. Let's say you have a normal distribution, it's parametrized by its mean and variance. If you have a latent variable model with n of these latent variables, you have an independent parameter for every latent variable, for the approximating term for every latent variable. So you have essentially n copies of these things that are independent parameters and you're optimizing directly over those. What you can do instead is something called amortized inference, where you don't give independent parameters for every possible element there for the latent variables, but instead you say that I have some function that is mapping the input itself to the parameters of that approximation, and it, of course, this function has some parameters. It's a bit kind of weird why we want to do this, but if you think about, for example, a case where you have 1 billion latent variables, each parameterized by a 2-parameter vector in and variance, then you have 2 billion parameters in your model. If the result, for example, if you look at yesterday's example of what is the actual update rule for a factor analysis model, you see that it's actually a linear function from the inputs to the parameters of this approximation. There's no point in having 2 billion parameters if you could just as well parameterize the linear function itself from the inputs to the parameters of the approximation. So you get a constant size parameterization that is independent of how many latent variables you have in your model. And you do that, of course, let's say, if you know that your result is going to be a linear function, you could plug it in as a linear function, but of course it could also be an arbitrary, let's say, a neural network that maps all of your inputs to the parameters of your approximation. This doesn't actually complicate anything. So if you write that my model parameter, the approximation parameters lambda, are obtained by this kind of a function from the inputs, then all the derivatives that you need for optimization, you just essentially end up concatenating, multiplying them with the derivative of this transformation with respect to its parameters. In terms of a code, there is almost, you just add this transformation there, automatic differentiation takes care of propagating gradients to the right thing. So you're just specifying your approximation with a very different kind of parameterization. A set of global parameters for the mapping inputs to the approximation parameters instead of every latent variable factor having its own parameters. You can think of this as just essentially, let's say, saving memory or possibly also computation speed, but it also leads to something you probably have heard of, so the variational autoencoder, which is not an autoencoder at all. I'll get back to that soon. So variational autoencoder is a simple latent variable model. You assume that you have some latent variables following a standard normal distribution, and your observations are some function, some nonlinear function, a neural network, mapping those latent variables into the observations. And what we want to do is we want to do variational approximation over these latent variables. So we want to learn Q of Z parameterized by some lambda. And we don't want to do this by introducing independent parameters for all of our latent variables, but instead we use the amortized inference idea. You have a function that maps your inputs to the means of your approximations. And you have another function that maps the inputs to the covariances of these approximations. This is simply just plugging in this amortized inference idea for this specific, very, very simplified probabilistic model. Here, if F and G mu and G sigma are all neural networks, then you have what is the variational autoencoder is doing. It is trained with the standard reparameterization gradients. This is actually one of the first papers that presents the reparameterization gradients as well. Not the very first, but one of the first ones. It's just presented in this very weird, somewhat kind of weird context of variational autoencoders. And I would really say that variational autoencoder is not an autoencoder at all. So an autoencoder is a thing where you feed in an input vector, you pass it through some sort of a lower dimensional representation, and you train your representation so that it should be easy to reconstruct the input itself. This is what, for example, what principal component analysis is this. It's a linear encoder followed by linear decoder, where the representation space is optimized to minimize the reconstruction error. Variational autoencoder is not this. There is no notion of taking an input and mapping it to the latent space. Instead, you assume that your latent variables follow some simple distribution. The encoding part is simply that the parameters of an approximation you put on these latent variables are functions of your inputs. So you're mapping your inputs to the parameters of this approximation. But that's just the technical thing. You could just as well parameterize each of your approximations independently. So we're not really doing an auto-encoding principle in here. It's postulating a simple probabilistic model using a very amortized variational inference for approximating the posterior over these data factors. As a probabilistic model, it's reasonable. It's a nonlinear extension of PCA, essentially. We don't do Bayesian inference over any of the parameters of these networks. They are just some arbitrary functions. But we do variational inference over the latent variables of this model. What it can do is that there's an arbitrary flexible mapping from the inputs to the parameters of the approximation. But the approximations themselves are still normal distributions. You have a normally distributed latent variable if you have an approximation that says it's a normal distribution. So it's a variational approximation with all the issues that you could have. But you can train it with stochastic gradient descent and so on. Finally, very, very briefly about what you can actually do with variational approximations and how should you do it. I thought about having lots and lots of slides about this and then decided not to. So we started earlier yesterday from the very basic observation that in the end, we want to compute some sort of expectations over the posterior. That's what we care about. We want to see what is the predictive distribution of our model if new data comes in, what is the accuracy for a classification problem for the new coming data, what is an optimal decision we want to do to maximize some utility that depends on data. And I said that this is easy. You just integrate over your posterior. And in some sense it is. So variational approximation, what you can do is that you just plug in your approximation in place of the real posterior. And now you can easily approximate this with the Monte Carlo. You draw samples from your approximation, you compute the value of this function of interest for all of these values, and you average over them. The issue is that this can have a huge bias. So if your approximation is bad, then this is certainly a bad approximation for the expectation as well. But this is still what people do. So this is how you would do it. So you first learn an approximation. Once you're happy with your approximation, you just use it in place of your posterior. This is, however, it's not the only thing you could do, and it's actually not the best thing you could do. A slightly better idea, something that has a lower bias, is to use importance sampling to estimate the expectation. So you draw samples from the approximation still, but instead of flat averaging over your samples, you compute the importance sampling estimator that reweights your individual samples. So every sample that is highly probable under the real model compared to the approximation, it gets increased weight in this approximation. It tries to kind of take into account the real model as well. Of course, this actually has a very large variance. So if you happen to draw a sample from your approximation, which has very low probability under the approximation, but every now and then you still get them. And then you have a relatively high probability under the real model for this parameter, then you get a weight that essentially can tend to infinity. You have some weight that has very, very high probability. So essentially then your expectation is going to be determined by this almost like an outlier sample, almost completely. This estimator does have a smaller bias, but it's relatively high variance. There is a better way. It's too complicated to be covered here, called Pareto smoothed importance sampling, from a recent paper that's essentially about evaluation of variational approximations. It is a generalization of the importance sampling estimator that tries to take into account that when does this estimator have finite variance, you can, for example, recognize that now I cannot estimate these expectations correctly. So go read that paper if you're going to actually use variational approximations for any realistic case. It really talks about the issues of, can I rely on this? Is it good enough? What should I do to estimate these intervals? I also wanted to list a couple of pointers to all the weird and fancy stuff that there was no hope of covering here. So I've been talking about the very fundamental basics. How do you do coordinate ascent variational inference? How do you do gradient-based learning for variational inference? And skipping like 95% of all the papers on variational approximation. They're trying to tackle all these small niches of doing something better than in the basic case. Now we've still been assuming mean field approximation all the time. That's actually much harder to get rid of than this conjugacy issue, which was solved by the gradients. There's some works on this that you build approximation families, let's say for a latent variable model, that you have an approximating family for the global parameters beta, and then you have an approximating family for every latent variable parameter, which is conditional on beta. So it's introducing some dependencies between your factorization, between the different elements in, but you're still making it essentially as a factorization. There's an idea on boosting variational inference. So if you already learned a variational approximation, you can, building on the idea of a standard boosting, you can recognize that in which parts of the parameter space it's bad. And then you add a new approximation, and you construct your real approximation as a mixture of these two. You keep on doing this, you keep on adding more and more mixture components into a mixture approximation, never kind of modifying the earlier ones. You just keep on reweighting them in some manner. So you can kind of improve your accuracy over time by learning better and better approximations. There's lots and lots of work on getting rid of KL divergence. There are other divergences that have nice technical properties. For example, you can reduce the effect of underestimating the variance by switching to another type of a divergence. I put here a link to a paper, a recent paper that essentially covers all of those, tells about the theoretical properties of those. A normalizing flow, if you heard about it, is essentially a way of constructing arbitrary approximating families by actually propagating density functions through a neural network. Not just the parameters of a density function, but really the actual real density function. So if every layer of a neural network has retains the volume of what you feed in, then you're actually propagating a density function. Collapsed hit sampling, you probably know of that. So in a hit sampler, if you can integrate out some variables analytically, it's much better than doing all the particular conditional on every other parameter. You can do something similar with variational inference, but not very easily. So you actually end up needing to approximate some terms there, but there's still some work on collapsed variational inference. We did one thing, a paper on this kind of way of reusing all the gradients that you've been computing for your model parameters. So to compute the derivative in a reparametrization with respect to the parameters of the approximation, it first computes the derivative of the model with respect to this theta n. And we could have sampled this theta n under that we've already computed, we could have sampled it also under our current new approximation. You can go on and borrow kind of historical gradient computations to speed things up by, let's say, an order of magnitude for simple enough models. Stained variational inference is about bringing in particle filter type of analogy to variational inference, so keep multiple particles and you're modifying those in order to get a better variational approximation. And then finally there's this partition PI. This is a very exhaustive paper, I guess, tens of pages of very technical stuff about how you can do this kind of modern, very scalable things like federated machine learning, distributing your variational inference computation on multiple machines, possibly without a centralized machine, which gets a bit complicated because of all the expectations and everything you do, but it can be done. And that's kind of one of the big things right now on scaling up variational inference for very big things. The take-home message for today is that you can do variational inference for a wide range of models by assuming a bit more about your model, and then of course compared to the coordinates and variational, you actually need to specify your approximating family as well. So that becomes part of your modeling workflow. You write your model and you write your approximating family as well. The important thing of making this automatic is that we can borrow a lot of technical stuff from what is currently being implemented in the deep learning frameworks. All the optimization algorithms, we can reuse them. All the automatic differentiation engines that are there, we can reuse them. You just need to write your loss function. In place of the loss functions, you write these expectations of the evidence lower bound. There's a lot of kind of going on in the intersection of the two. So the variational autoencoder is a classical deep learning model that is actually also variational approximation for a very simple Bayesian model. So I do see that, I mean, also in terms of the software, so TensorFlow probability, Pyro, AI, they are tools that kind of merge a lot of the concepts in deep learning and Bayesian inference. The variational approximation is a very practical approach there. It's rather hard to merge MC-MC and these kind of deep neural networks there as functions. But compared to what we talked about yesterday, there is a cost. So we're going from very elegant, simple coordinate asset rules that are trivially will converge to a local optimum. They are computationally relatively efficient, very easy equations to write once you know the conditionals. We're moving from this very constrained, nice world to the dirty world of kind of stochastic optimization. There are all the kind of weird hyperparameters of which step length scheme you use, what is the initial step length, how do you initialize your approximation, how do you make sure that you're doing it well. All the papers make it sound easy. So you have a research paper that says just use stochastic gradient descent. There is actually a similar kind of an effort as in a deep learning research on figuring out how do I actually optimize my current problem well. And sometimes, yeah, we also have this kind of a computational cost coming from the need of doing lots and lots of iterations of this stochastic gradient descent compared to possibly tens of iterations of the coordinate ascent algorithm. Then there's still 3 slides of the references, so you can go and read all of those in the evening if you want. That's all I had for now.